Hello everyone, welcome back. In this video, we're going to talk about simplifying radical expressions. And so let's start by being really clear what we mean by a radical expression. So it's very likely that we've encountered things like square roots or cube roots before in our mathematical experience. Radicals or radical expressions are just another way to describe these quantities. So in general, if we have these root symbols like the square root of some quantity or the cube root of some quantity, those are referred to as radicals. Being able to work with these roots or these radicals are really important. They show up all the time, especially when we're trying to solve for the base in simple equations like x squared equals 25 or x cubed equals 125. In order to find the solutions to these equations, we usually end up using something like a radical or a root. So let's go ahead and look at some quick examples using this root and radical notation. Let's make sure that we know what this notation is asking of us, and also that we know how to check our answers when we evaluate this notation. So for example, let's go ahead and look at some simple square roots. Here we have the square root of 9, the square root of 16, as well as the square root of 25, and we want to evaluate these three expressions. So what is the square root of 9? What is that asking of us? Well, when we see an expression like the square root of 9, it is asking us what number do we have to square or raise to the power of 2 such that when we square or raise that number to the power of 2, we end up with 9. And well, that number is going to be positive 3. And so the square root of 9 is equal to positive 3 because when we take 3 and raise it to the power of 2, we get 9. So one way to think through evaluating a square root expression is by thinking of what number do I have to raise to the power of 2 to get the number inside of the square root? That is what the square root is asking for us. What number do we have to raise to the power of 2 to get the number inside? And we can always check that by taking our answer, raising it to that power of 2, and seeing that we get that number that was inside of our square root or this radical. So similarly, if we want to evaluate the square root of 16, we have to think through all these numbers out there such that when we raise this number to the power of 2 or multiply it by itself, we get back to 16, and well, that number is going to be positive 4. And so the square root is asking us to find this number that when raised to the power of 2 gets us back to 16, and we can check our answer in our work by doing just that. If we take our number 4 and raise it to the power of 2, 4 times 4 is in fact equal to 16. So 4 must be the square root of 16. Similarly, if we're asked to evaluate the square root of 25, this is really asking us to find the number such that when we raise it to the power of 2, what comes out is 25, and well, that number should be 5. And just checking that, 5 raised to the power of 2, or 5 times 5, is in fact equal to 25. So 5 is the square root of 25. And so when we're trying to evaluate or simplify these square roots, it's often really helpful to think about all the different powers of 2 of some of these smaller numbers, usually like 1 through 10 or 1 through 12. Having a table of perfect squares like 1 squared, 2 squared, 3 squared, 4 squared, and so on to reference can be really helpful and help expedite this process. And the process is very similar when we're working with cube roots or these higher roots. We just have to tweak our thinking just a little bit. Instead of thinking about those numbers that we have to raise to the power of 2, to get the number inside or underneath our radicals, for cube roots, we have to think about the number that we have to raise to the power of 3 to get the number inside or underneath our radical. So this expression is read as the cube root of 8, and what it is asking us to find is that special number that when we raise it to the power of 3, out comes 8. And so, well, 2 is that number. So to evaluate the cube root of 8, we can write that as 2, and we can check this because if we take the time to raise 2 to the power of 3, we should get the number underneath our cube root or underneath this radical, and that will be 8 because 2 times 2 times 2 is in fact 8. And so we can do this for all these other cube root expressions as well. The cube root of 27 is asking us to find the number that when we raise it to the power of 3 is equal to 27, and that number just so happens to also be 3. And we can check this because 3 to the power of 3, or 3 times 3 times 3, is going to be 27. The next one on our list is asking us to find the cube root of 64. This might start getting a little bit trickier. And again, having a table to reference can be really, really helpful for this process. And so we can just look up or create this table that shows all the different powers of 3 of our small integers. And if we do that, we should end up finding that 4 raised to the power of 3 is 64. and that is exactly why the cube root of 64 is equal to 4. And so for this final expression we have in this example, we're asked to evaluate the cube root of 125. That's asking us to find that number out there that when we raise it to the power of 3, we get 125, and that number just so happens to be 5. And again, this is just our way of kind of verifying or checking our work here, making sure we're understanding what this notation is asking us. And what we're seeing here is that if 5 is the cube root of 125, then if we raise 5 to the power of 3, that should give us 125, and it does. And so in those first sets of examples we just looked at numbers that we could find the square root or cube root of. These were numbers that were perfect squares or perfect cubes. However, not every number that ends up underneath a radical will be a perfect square or a perfect cube. And so next we want to talk about how to simplify those types of expressions and how to make them easier to work with. And so here I have an example of one of those types of expressions. Here we want to simplify the square root of 18. And so what we were doing earlier won't quite work because there is no nice integer or whole number that we can think of that when we raise it to the power of 2, we get 18, right? 4 to the power of 2 is 16, that's kind of close, but then 5 to the power of 2 is 25. So there is no whole number or integer that when we raise it to the power of 2, we get 18. And so just because 18 is not a perfect square does not mean that we can't break it down and make it easier to work with. And that's what we're going to try to do when we are attempting to take these square roots or cube roots or radicals of these non-perfect square, perfect cube, or perfect powered numbers. Essentially what we're going to do is break this number down into its pieces that are perfect squares, and then its pieces that are not perfect squares. And in order to help us do that, we have to use this very special property of radicals or roots, what we call the product property for radicals. Okay, so here I have the product property for radicals written on the board, and this is the version for square roots, and we're looking at the version for square roots because that's what we run into most often. And so what this product property for radicals is trying to communicate is that if we're taking the square root of some number that we can think of as a product of two other numbers or quantities, then we can actually factor that as the square root of the first number or quantity multiplied by the square root of the other number, factor, or quantity. And for square roots and even roots, we do have this important note that this kind of separation can only happen as long as both of these factors or numbers are positive or greater than 0. So how is something like the product property for radicals going to help us simplify an expression like the square root of 18? Well, let's go ahead and check it out. So we're going to take our square root of 18 and think of that as the product of two numbers that we don't know yet, x times y. When we're thinking about what these two numbers x times y could be, we want to be very thoughtful in our choices. For the first number, we want to think of what is the largest perfect square that 18 is divisible by, or the largest perfect square that is a factor of 18. And it might be helpful, especially for larger numbers than this example, to list out some of those perfect squares or perfect cube roots if you're working with that type of radical, and then you can reference those as you're trying to figure these numbers out. So some of our early perfect squares are like 4, 9, 25, and 36. And so we think, are any of those numbers factors of 18, or is 18 divided by or divisible by any of those numbers? And if we think through it, 9 should be the one that jumps out at us. We can think of 18 as 9 times 2. So applying that factoring of 18 as 9 times 2, along with this product property for radicals, allows us to rewrite the square root of 18 as the square root of 9 times the square root of 2. So what we've really done is we factored the square root of 18 as these two factors, the square root of 9, which is a perfect square, and the square root of 2, which is our non-perfect square factor. And so now we can evaluate the square root of 9, and we just have to think of what number, when raised to the power of 2, gives us 9. That number will be 3. So we simplify the piece that we can, but then for the other factor or piece that cannot be simplified, we just rewrite that. And so our final answer, the simplified form of the square root of 18, is going to be 3 times the square root of 2. So eventually we'll be doing all kinds of arithmetic with these radical expressions, and writing them in a simplified form like this will be really useful, especially when we're trying to cancel common factors between these expressions, or when we're trying to add, subtract, multiply, or divide these expressions. All right, let's look at one more example of simplifying some complicated square roots before we move on to cube roots. And so in this example, we want to simplify the square root of 108. And so ideally, we want to write this as the product of two square roots, where that first square root is the largest perfect square that 108 is divisible by, and the second square root just contains those leftover non-perfect square factors. But sometimes we may not find the largest perfect square that the original square root is divisible by, in which case we have to kind of do this process multiple times until we whittle it all the way down. So I want to illustrate that in this example. So the largest perfect square factor of 108 ends up being 36, but maybe we're referencing our table and we don't see that right away. Maybe we find a smaller perfect square before we get to 36. So for example, 108 is also divisible by 4. And since 108 is divisible by 4, we can write the square root of 108 as the square root of 4 times the square root of 27. And so now we have broken down the square root of 108 as a perfect square, the square root of 4, times a non-perfect square, the square root of 27. We can evaluate the square root of 4 and turn that into a factor of 2. And now our expression is looking like 2 times the square root of 27. So we have simplified this, but we have not simplified it all the way. So to finish simplifying our expression all the way, we have to re-examine our square root of 27 and think through our process again. Is there a perfect square factor that 27 is divisible by? And there is. So we can't ignore or forget about that factor of 2 out front, but now we have to re-break apart or refactor the square root of 27. This time, the only way we can break it down any further is to think of it as the square root of 9 times the square root of 3. And so now if we simplify that perfect square factor of the square root of 9, that'll turn into a factor of 3. And we still have that irreducible square root of 3 hanging out at the end. And so now just to totally finish this example off, we're almost done. We can multiply these two factors of 2 and 3 together out front, and that'll turn into a factor of 6. And so our final answer, the most simplified form that we can write the square root of 108 in, is 6 times the square root of 3. And again, this is just an example of showing what the process might look like if we don't identify the largest perfect square right away. But if we did identify that largest perfect square right away, we get to the same final result, right? We can rewrite the square root of 108 as the square root of 36 times the square root of 3. And now we can take that square root of 36, because it is a perfect square, that simplifies to 6. Then we just have our leftover factor of the square root of 3 hanging out. Either way we cut it though, this simplifies to 6 times the square root of 3.